The focus of my video tutorial is on the series parallel combination of resistances. So stick around. So before we analyze our given problem, let us first review important formulas or equations. For determining the current in a series circuit, all right, we just apply the fact that the individual currents is just equal to the total currents. At any given point in a series circuit, the current is said to be constant. Okay, now for parallel circuit, if you want to get the total current, you just add the individual currents. That is, total current is equal to I sub 1 plus I sub 2 plus whatever is the number of currents. Alright. For voltage, we have this formula for determining the total voltage in a series circuit. Vt is equal to V sub 1 plus V sub 2 plus V sub n. Alright. Now for parallel circuit, we say that in a parallel circuit, the total voltage and the individual voltages are just equal. Alright, so each and every voltage across the circuit, we say, are the same. Now for determining the resistance, total resistance in a series circuit, we also add the individual resistances such as R1 plus R2 plus R sub n. Okay, but for parallel circuit, we use the reciprocal formula in determining the total current. That is, 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R sub n. So that's it. That's the formula for the parallel resistance, total resistance. There are two important shortcut formulas when you want to determine the sum of two resistances that are connected in parallel. Alright? So if the resistances, the two unequal resistances are connected in parallel, we just use the formula R sub 1, 2 is equal to the product over the sum. Okay, and that is R1 times R2 divided by R1 plus R2. Now, if the two resistances connected in parallel have equal values, all right, for two or more equal resistances in parallel, all we have to do is just divide the given R by the number of resistances there are in the circuit. So these are the important equations for analyzing series and parallel resistances. So this is our given problem. In the given direct current circuit shown in this diagram, we are going to calculate the total resistance in the circuit, the total current, the individual current through each resistor, and the individual voltages across each resistor. Alright, so this is the circuit diagram, right? The given voltage supply or total voltage is 12 volts. Okay, so the individual resistances are also given, such as R1 equals 2.00 ohms. R2 over here is equal to 4.00 ohms. This is R3, which is equal to 6.00 ohm. This is R4, which is equal to 3.00 ohm. And this one here is R5, which is equal to 6.00 ohm. Alright, so in a circuit like this, as you can see, the resistances are connected in series and in parallel combination. All right. For example, what can you say about R1 and R2? Are they connected in series or are they connected in parallel? The answer is neither. They are not connected in series. Okay, neither are they connected in parallel. Okay. How about R3? R3 and R2, for example. Okay, is R3 here connected in series with R2? The answer again is no, they are not. Okay, they are not connected in series. Neither is R3 connected in parallel to R4. But what is sure, or what we are sure about, is that R4 and R5 are definitely connected in parallel. All right? So they are exactly parallel to each other. Now, the solution that we are going to apply is we are going to start from the outermost. Okay? From the outermost resistors or resistances. When you say outermost, the very far, all right, the very far uh, resistances will be combined first. Okay, we cannot start by adding R1 and R2 because we don't know if they are in series or in parallel. The fact is they are not. All right, but since we know that R4 is parallel to R5, then we can start combining R4 and R5 using the concept of adding two resistances in parallel. And that is what we are going to show in the next slide. We saw that in the earlier slide, we had R4 and R5 connected in parallel. All right? So when they are combined, using the formula in adding two unequal resistances in parallel, this is what will happen. Okay? We say the sum of R4 and R5, which is denoted as R sub 4 and 5, okay, we just multiply the two R's, R4 times R5, and then divide them by the sum of the two R's, or R4 plus R5. And that means R4, R sub 4, 5 is just equal to 3 ohms times 6 ohms. Okay, that is supposed to be 6 ohms. All right, I forgot the decimal point. And then divide it by their sum. 3 ohms plus 6 ohms, and you will get as the sum of R4 and R5 equals 2.00 ohms. All right, and what that particular sum of the two parallel resistances, okay, is now represented by this zigzag. All right, symbol. The zigzag symbol represents already the sum of R4 and R5 that has been computed to be equal to 2.00 ohm. All right. Now, you, if you look at carefully how R3 and R45 are connected, obviously they are connected in series. All right. They are now connected in series because there is only one path for current to flow between the two of them. All right, between R3 and R45, that is the only way for the current to move from R3 to R45 or from R45 to R3. So we say therefore that the two resistances R3 and R45 are connected in series. Right? So the next solution therefore is to combine R3 and R45. Okay? Simply using the formula for adding two resistances in series. But that will be shown in the next slide. Alright, so we already said that R3 and R45 are now connected in series. So their sum therefore can just be determined by adding them directly. Alright? We call this the sum of R3 and R45. We call it now as R345. And that is equal to the sum of 6 ohms plus 2 ohms. Of course, the sum is 8 ohms. Alright? So the combination of these two that we just combined becomes 8 ohms. And then from there, we will proceed, look at how that sum of R3 and R45. The moment they are combined, we'll be calling it now as R3, 4, and 5. And we will see how that combination is connected to the next R, which is R2. That's coming in the next slide. So, the sum of uh, the two resistors that we just computed earlier, we call it now the R sub 3, 4, and 5, whose value is 8.00 ohms. And if you look at the diagram now, okay, this zigzag sign represents that particular resistance equivalent to, labeled R3, 4, and 5. How is this connected to the second resistor R2? Obviously, they are in parallel. And therefore, when we add them, we use the formula for adding two unequal resistances in parallel, which is simply the uh, product over their sum. Okay? Since R2 is 4 ohms multiplied to 8 ohms, which is the value of R3, 4, and 5, and then divide them by the sum of 4 ohms and 8 ohms. And this is what? 4 times 8 is 32 ohm, alright? Or 32 ohms squared, if you wish. Alright? 32 ohms squared divided by what? 12 ohms. So the ohms cancels out. The ohm squared divided by ohm will give us, of course, ohm. But 32 divided by 12, of course, will give us the value of 2.67 ohms. So what do we call this now? This is now the resistance combination of R2, R3, R4, R5. Okay? All the four resistances were combined or have been combined as one, and the sum is equal to 2.67 ohms. So that total R2, 3, 4, and 5 will now be added to the next remaining resistance, which is R1. Okay, and our computation will be shown in the next slide. Alright, so now, as you can see in the simplified circuit, we are left with two resistors or resistances, such as R1 equals 2 ohms, and the combination of Rs 2, 3, 4, and 5, which is now equal to 2.67 ohms. And obviously, as you can see, okay, there is only one path for current to flow between R1 and R2, 3, 4, and 5. So definitely these two resistors or resistances are combined in series. Alright? And so therefore, when we add them, we just use the formula for getting the total resistance for series resistors. That is, the combination of resistors R1, 2, 3, 4, and 5, alright, is equal to 2 ohms plus 2.67 ohms. And of course, that gives us 4.67 ohms. All right. And since we just added all the resistances, okay, we also call this the total R or R sub T. Okay. So what do we do next? We'll see in the next slide. All right. So what we have now is the most simplified circuit diagram where the zigzag symbol, okay, represents all the combination of the resistances that we just added, which is equal to 4.67 ohms. Okay, this is the total resistance for the whole circuit. Okay, and the voltage supply, which is labeled V sub T, and that is equal to 12 volts. Of course, uh, since we're looking for the total current in the circuit, we can now just use Ohm's law to determine the total current. That is, simply divide, all right, simply divide the total voltage by the total resistance. That is 12 volts divided by 4.67 ohms, and that will give us 2.57 amperes. This is the total current generated, okay, by the voltage supply of 12 volts. Okay, so we can imagine the current, okay, using the conventional flow of current. So we can imagine the current from the positive terminal, the battery, to be moving like this in a counterclockwise direction. All right. So when it passes through this resistor that represents the total resistance, okay, the current through this resistor, we say, is equal to 2.57 amperes. So that is how we visualize, all right, the flow of charge considered a positive charge, okay, and not the flow of electron. If you are aware that of the difference between the two, okay, so when we use the flow of positive charge, it must be from the positive terminal, okay, going through the circuit and then ends up at the negative terminal. We call that the flow of positive charge. That is the conventional flow of current. But if you choose the so-called electron flow, where you start from the negative end or the negative terminal of the battery, all right, this will be the what we call electron flow. From the negative, passing through all the resistors, and then back to the positive terminal. Okay? So it's up to you what current convention you are to follow. Doesn't matter. Okay, so what do you do next now? Alright, aside from getting the total current, which is now equal to 2.57 amperes, no? We are going to determine the individual currents. But this time, okay, we are going to sort of go back, alright, go back to uh, what we call the resistances that are far from the source. Okay, far from the source, starting with I sub 1, R sub 1. Remember this resistor represents the total. Okay, so in the next slide, okay, we will go back to the individual resistors, starting with R1, and that is now in the next slide. So our technique in determining the individual currents is just to sort of go back, all right, starting from R1 until we are able to combine or to see how the currents as well as the voltages can be added, okay, until we reach the last two resistances that we saw earlier, right? So for now, in the diagram, we only see the two resistances R1 and the combination of R2, 3, 4, 5, whose value is equal to 2.67 ohms. That of R1 is 2.00 ohms. All right. And this is how we are going to find the current as well as the voltages for each. Okay, we already said that the total current was computed to be 2.57 amperes. And you will notice that the total current generated by the battery is also equal to the current that passes through R sub 1. The mere fact that R sub 1 is in series to the battery. So that makes the current through R1 equal to the total current. We say that I sub 1 is also equal to 2.57 amperes. And since R sub 2, 3, 4, and 5, okay, is also in series with R1, and therefore, whatever is the current that passes through R1 is the same current that passes through R2, 3, 4, and 5. That's why we also equate to I sub 1 and I sub t, okay, the current through R or I through R2, 3, 4, 5. We call it the current I2, 3, 4, 5. So both I1, okay, and I sub 2, 3, 4, 5 are equal to 2.57 amperes. That's for the current. And we use the concept of resistors in series, okay, where it says that the current in series circuit is always constant or the same. Now, what else? For the voltage, okay, for the voltage, we use again the concept of Ohm's law. All right, since we know already the current I sub 1, all right, we just multiply it by R1. So I sub 1 is 2.57 amperes. Multiply it by the given resistance of R1, which is 2.00 ohms, and what we get is 5.14 volts. This is the voltage across resistance R1. Alright, now since we also said that I sub 2, 3, 4, 5 is equal to 2.57 amperes, using Ohm's law once again, multiplying I sub 2, 3, 4, 5 by the equivalent resistance R2, 3, 4, 5, alright, and substituting 2.57 ampere multiplied by 2.67 ohms, what we get is the voltage across this resistor or resistance V2345 equals 6.86 volts. Alright, so at this point, okay, we already know what is the current through R1 as well as the voltage across R1. Okay, what we want are the individual currents and voltages. For R2, 3, 4, 5, okay, whose voltage is equal to 6.86 and whose current is 1 or 2.57 ampere. That represents the current and voltage, okay, for this combination. So that will still have to be simplified. And that you will see the next step, of course, in the next slide. Alright, so earlier we already determined the current and the voltage for R's of 2, 3, 4, 5. All right. So R2, it follows that R2, whose value is 4 ohms, okay, this is part of that combination earlier. R2 is part of that combination R2, 3, 4, 5. And we can use the fact that uh, the voltage, okay, in a parallel connection, the voltage Vt is equal to the individual voltages. That is what's shown by here by this equation. V2, which is part of V2, 3, 4, 5, all right, that we just added uh, and represented earlier by 2 B2, 3, 4, 5. Okay, they are in fact parallel. Okay, that's how we are able to say that the value of V sub 2 is also equal to the value of the sum of the voltages of V2, 3, 4, 5 because they are in parallel. So our conclusion is that V sub 2 is also equal to 6.86 volts earlier computed. Okay, so we make use of that again using Ohm's law to find the current through R2. All right, wherein I2 is equal to V sub 2 over R2. Substituting, we have 6.86 volts divided by the given resistance of 4 ohms, 4.00 ohms. And what we get is the current 1.72 amperes. This is the current through R2. All right. So that means for resistance R2, its current through it is equal to 1.72 amperes and the voltage across it is 6.86 volts. So I'm sure you know what's going to happen next. All right. This R2345 will now be broken down further. All right. What's next to R2? Of course, is R3. Okay. But the computation for the current and the voltage across R3 will be shown in the next slide. All right. So when we break down uh, the earlier sum of resistances R2, 3, 4, 5, okay, uh, this is how our circuit diagram now looks like. No? There is the combination of R's 3, 4, and 5 represented by the zigzag, and of course the preceding what we call zigzag symbolizing R sub 2. All right. And obviously, since they are parallel, we can use the fact that in a parallel combination or in a parallel circuit, all right, the voltage, the total voltage will be just equal to the individual voltages. So that's what we're going to use to determine what voltage is across V sub 2, although we already computed that or determined that earlier, all right? But with the help of V sub 2 being equal to 6.86 volts, okay, uh, since they are parallel to V2, as shown, okay, we can conclude that the voltage of V sub 345 is also equal to 6.86 volts. All right, using the concept of parallel um, resistances, where the voltages of the individual voltages is equal to the sum, the voltage sum. So using that Ohm's law again, we can determine what the current through R3, 4, and 5. We call it I sub 3, 4, and 5. Okay, and just substitute since the given voltage V345 is equal to 6.86 volts, and divided by the given resistance here, R3, R3, 4, and 5, which is 8 ohms, 8.00 ohms. So what we determine here is 0.858 amperes. This current is the current that flows through this combination of resistors or resistances R345. That's all that we can have, okay, here. For the next resistor, all right, which is R3, okay, we will see the computation for I sub 3 and I sub or V sub 3 in the next slide. All right, so knowing the current and the voltage that went through R sub 345, we can use that to determine the current through R3 as well as the voltage across R3. Okay? I sub 345 was earlier determined as K equal to 0.858 amperes because we divided 6.86 volts. This is the voltage across R345 earlier, and dividing it by the corresponding resistance, which is 8.0 ohms, that's how we got 0.858 amperes. But since R3 is in series, all right, it is in series with uh, R45. Okay, this is now R45. Therefore, we make use of that concept that the current across I3 is also the same as the current across I sub 345. Hence, the voltage across R3 can now be determined using Ohm's law. Alright, we just divide or we just multiply the current of 0.858 amperes by the given resistance of 6.00 ohms. So what we get is 5.15 volts as the voltage across R3. And in this circuit now, all right, R45, which is 2 ohms, okay, is as shown, appears to be in series with R3, right? So our next step, therefore, will show us determining the current across the current through R45 as well as the voltage across R45. So as shown in the diagram, R3 is in series with R45. So it follows that whatever is the current through R3, which was earlier determined, will also be the same current through R45. And from there on, we can determine the voltage across R45. Here it is. Alright, R3 and R45 are in series. So we just say that the current across I3 earlier computed as 0.858 ampere is also equal to the current through R45, and that is labeled as I sub 45. Using that current value, we use Ohm's law again to determine the voltage across V45, meaning 0.858 amperes is multiplied to the given voltage, the combination of R4 and R5, which is 2.00 ohms, and we get the voltage equal to 1.72 volts. This is the voltage across this combination of R45. So, uh, coming the last slide will be the last portion of our circuit determining the current through R4 as well as R5 and their individual voltages. So, as you can see, this is the original circuit diagram that we had at the beginning of our discussion. Alright? And earlier, we already determined the voltage across the combination of R5 and R4 as well as their what you call the current across the combination of R5 and R4. Now, we make use of that to determine the individual currents through each of R4 and R5 as well as their individual voltages. Right. So in our solution, since R4 and R5 are in parallel, okay, previously we already determined that V sub 45 is equal to 1.72 volts. And that means if this is the sum of the voltages of V4 and V5, it follows that that sum is also equal to the individual voltages. That's why we equate here, this value is equated to V4 as well as to V5 because individually R4 and R5 also have or has this voltage across each of them. So the last part of the solution is to determine the current through R4 as well as R5. And to compute for I4, of course, using Ohm's law, we just substitute V4, which is 1.72 volts, and the given resistance of R4, which is 3.00 ohms. Hence, we get the current through it, which is 0.573 amperes. And for I5, that's also equal to V5 divided by R5, which is by substituting 1.72 volts divided by 6.0 ohms, or a current equal to 0.287 amperes. So these are the values of I sub 4 and I sub 5 as well as their voltages. V4 and V5 each being equal to 1.72 volts. Right? Before we end, we will see the summary of our answers in the next slide. So hang on. We will now summarize the results in this table. Alright, so we are given the individual currents through each of the resistors, alright, as well as the voltages across each resistor. So they're all here. And of course, we also have the total resistance, R sub T, and the total current. You notice that the total current is equal to the current through R1 because according to the diagram, it's only R1 that is directly in series to the battery. Alright? So, I hope this method of determining the individual currents as well as the individual voltages for this kind of circuit, okay, some people call this a circuit network. Alright? So, in the second part of my video or tutorial video, I will be uh, explaining also another method of determining the the individual currents as well as the individual voltages for a network, all right, using what we call Kirchhoff's rules. So I hope you'll stand by, okay, for that particular video tutorial. So for now, thank you very much and have a good day.